Hey everyone, and welcome to our deep dive on math fundamentals. We're going to be unlocking some core concepts from this guide that's someone sent to us, which is awesome if you're like looking for a refresher course or, maybe just discovering some hidden math gems.
Yeah, and math can be pretty intimidating for a lot of people, but we're not here to turn you into mathematicians overnight.
Right.
What we really want to do is show you the why behind the formulas.
Yeah.
Because once you see the logic behind it, it's not just like a bunch of rules, it's actually pretty useful.
Yeah.
And maybe even, I dare say, fascinating.
Okay, so let's dive right in. First up, we're starting with set theory.
Okay.
And I remember sets being about like collections of things.
Right.
Like you could have a set of all the planets in the solar system.
Yeah, that's a great example. And it's really interesting about sets is this concept of the power set.
Okay.
It's like a set of all the possible subsets you can create from the original set.
So it's like a set with sets inside.
Ex
Okay, wait. How many subsets can you even make from a set with like just two things in it?
Okay, so let's say our set has the numbers 1 and 2.
Okay.
Now, the power set of that would include the empty set,
Yeah.
which is always a subset.
Okay.
The set with just 1, the set with just 2,
Right.
and then the set with both 1 and 2. So that's 4 subsets total.
Wow. Okay, that's more than I would guess. So why is the power set important?
Yeah.
Is it just like a mathematical brain teaser or something?
No, not at all.
Mm.
The power set is actually a fundamental concept in math.
Oh, wow.
Computer science, and even logic.
Wow.
Like every time you make a choice to include something or to leave it out,
Okay.
you're essentially dealing with a subset.
Right.
So this pops up everywhere from coding algorithms to analyzing data.
That's so cool. So it's like it gives you like a framework for thinking about all the different possibilities.
Exactly.
Yeah. Okay. And speaking of exploring possibilities,
Hmm.
what about other operations we can do with sets?
Right. So you've got a union, which is like combining two sets together.
Okay.
You've got intersection, which is finding the elements that belong to both sets.
Mm-hmm.
You've got difference, which shows you like what's unique to one set
Okay.
compared to another.
Gotcha.
And then you've got the complement,
Okay.
which includes everything outside of a specific set,
Right.
but still within like a larger universal set.
Oh, okay. Okay.
Okay.
So if like I have a set of all the even numbers and a set of all the prime numbers,
Mm-hmm.
their intersection would be just the number 2
Exactly.
because it's the only even prime number.
Yeah, you got it.
Okay.
And these operations are super helpful for visualizing relationships.
Right.
Have you ever seen a Venn diagram?
Yeah.
Those overlapping circles?
Yeah. Yeah.
That's a great way to see how sets interact.
Yeah. Venn diagrams are cool.
Yeah.
They make it much easier to like grasp. Okay. So we've explored sets and how they work. Ready to move on to the numbers themselves?
Absolutely.
There's so many types of numbers.
Yeah.
Natural numbers, whole numbers, integers,
Mhm.
rational numbers, irrational numbers. It's kind of overwhelming. What's the difference between a rational and irrational number again?
So think of rational numbers as any number that can be written as a fraction,
Okay.
like 12, 34.
Right.
Irrational numbers, on the other hand, can't be expressed as a simple fraction.
Okay.
So like a classic example is the square root of 2.
Right. I remember that being like a big deal in ancient Greece or something.
It was, yeah. It really shook things up for those mathematicians back then.
Oh, wow.
Like it challenged their whole understanding of numbers,
Yeah.
and it forced them to come up with new ways of thinking about math.
That's fascinating. It shows you how even like seemingly simple concepts
Yeah.
can lead to these like big breakthroughs. Speaking of which, how do we work with square roots?
Yeah.
Especially when they show up in the denominator of a fraction. Like what if we have 1 divided by the square root of 2?
That's where we use this concept of rationalizing the denominator. It's a technique to simplify expressions by getting rid of those pesky square roots in the denominator. So in your example, we would multiply both the top and bottom by the square root of 2. And that gives us the square root of 2 divided by 2.
Oh, okay. That makes the expression much cleaner.
Exactly.
So we've covered sets, different types of numbers, and even a bit of algebra. What's next on our mathematical adventure?
Well, welcome back, everybody. Hope you're ready for some more mathematical insights because we've got a lot to cover today.
Definitely. I'm really starting to see how all these like seemingly abstract concepts
Right?
connect to like the bigger picture. It's like we're building this mathematical toolkit
Yeah,
that we can use to understand the world around us.
that's a great analogy. And speaking of toolkits, let's add another powerful tool to yours.
Okay.
The concept of intervals.
Intervals, like a range of values.
Exactly. In math, an interval is a set of real numbers that contains all numbers between two given values.
Okay.
They're incredibly useful for representing solutions to inequalities and for understanding the behavior of functions.
Okay, I'm intrigued. What kinds of intervals are there?
Well, you have closed intervals,
Okay.
which include both endpoints, and we write those using square brackets. So, for example, the interval from 2 to 5,
Okay.
including both 2 and 5, would be written as 2, 5.
So it's like a line segment on the number line.
Exactly.
From 2 to 5 with both endpoints filled in.
Yes. Then you have open intervals,
Okay.
which don't include the endpoints, and we use parentheses for those.
Right.
So the interval of numbers between 2 and 5,
Yeah.
but not including 2 and 5 themselves, would be 2.
So it's like the same segment on the number line,
Right.
but with like open circles at the endpoints?
Exactly.
Okay. What about intervals that include one endpoint but not the other?
Those are called half-open or half-closed intervals.
Oh, okay.
And we use a combination of a bracket and a parenthesis to show which endpoint is included.
Okay.
So, for instance, 2, 5 includes 5 but not 2. And 2, 5 includes 2 but not 5.
Got it. So how do these intervals actually help us understand math? Are they just a fancy way of writing down a range of numbers?
Not at all. Intervals are incredibly powerful for visualizing and solving inequalities.
Okay.
Remember our example from earlier, x plus 2, 5?
Mm-hmm.
The solution, all x greater than 3,
Right.
can be neatly represented by the open interval 3, infinity.
That's really helpful. It's like they give us a shorthand for expressing those solutions.
Exactly.
And I guess they're also useful for describing like the domain and range of functions, right?
Absolutely. The domain is the set of all possible input values for a function, and the range is the set of all possible output values.
Okay.
And both can be expressed using intervals. But for now, let's stick with our exploration of basic operations with intervals.
Okay, like what?
Well, we can find the union of two intervals, which
Absolutely.
includes all the numbers that are in either one or both of the intervals.
So if we have the interval 1, 4 and the interval 3, 6,
Mm-hmm.
their union would be everything from 1 to 6.
Almost. It would be 1, 6.
Ah.
Because we only include the left endpoint 1.
Right, because the 6 isn't included in the second interval.
Exactly.
Okay. And what about finding like the overlap between two intervals?
That's called the intersection.
Okay.
And it includes only the numbers that are present in both intervals. So the intersection of 1, 4, and 3, 6
Okay.
would be 3, 4.
This is starting to feel familiar. It's like we're using the same kind of logic that we used with set operations.
Right.
But now we're applying it to like ranges of numbers.
Exactly. And just like set operations, these interval operations have practical applications.
No, cool.
In fields like data analysis, computer programming.
Okay.
They even pop up in everyday scenarios.
Wow.
Like figuring out overlapping schedules
Oh, right.
or budgeting within certain limits.
Okay, my mind is officially blown. Intervals are way cooler than I ever imagined.
I'm glad you're seeing their power. And trust me, we've only scratched the surface.
Wow.
As we explore more complex mathematical topics,
Yeah.
you'll find that intervals are indispensable tools for representing and manipulating numerical data.
I can't wait. Speaking of more complex topics,
Yeah.
are we ready to tackle indices and surds? Those always seemed a bit mysterious to me.
Let's dive in. Indices, which you might know as exponents,
Right.
are simply a shorthand way of expressing repeated multiplication. So, for example, instead of writing 2 by 2 by 2 by 2,
Right.
we can write 2 raised to the power of 4,
Okay.
or 2.
Right. The little number above the 2 tells you how many times to multiply the base,
Exactly.
which is 2 in this case. But why are there all those special rules for working with indices?
Those are the laws of indices.
Okay.
And they are crucial for simplifying expressions and solving equations involving exponents. So, for instance, when you multiply two powers with the same base,
Okay.
you simply add the exponents. So 2 other times 2 IL equals 2i.
Okay, that makes sense. It's like combining all those repeated multiplications
Back up.
into a single exponent. What about when you divide powers with the same base?
Then you subtract the exponents.
Okay.
So 2r divided by 2n equals 2n. And when you raise a power to another power,
Okay.
you multiply the exponents. So for instance, 2n
Okay.
equals 2n.
Ah, I see the pattern.
Yeah.
It's all about like manipulating those exponents according to specific rules.
Exactly. And these rules aren't just arbitrary.
Right.
They're based on the fundamental properties of multiplication and division. And as you get deeper into math, you'll find that indices are incredibly useful for dealing with very large or very small numbers, like those involved in scientific notation or financial calculations.
Right, like expressing the distance to a star or the size of an atom.
Exactly.
In a way that's like easier to work with.
Exactly.
Speaking of different types of numbers, how do surds fit into all this?
So surds or roots are essentially the inverse operation of raising a number to a power.
Okay.
So, for example, the square root of 9 is 3.
Right.
Because 2 times 3 equals 9.
So it's like going in reverse.
Exactly.
But why are some surds considered tricky?
Well, some surds, like the square root of 2, result in irrational numbers.
Okay.
Those numbers that can't be expressed as simple fractions. And remember, not all irrational numbers are surds.
Right.
It's all about understanding the subtle relationships between different types of numbers.
Right. Those nuances are what make math so fascinating.
Yeah.
It's not just about memorizing formulas.
Right.
It's about understanding the intricate connections between different concepts.
Exactly. And how about we tackle one more concept before we wrap up part 2?
Sounds good. What did you have in mind? Okay, so we've covered sets, different types of numbers, intervals, indices, and even touched on surds. What else is there to explore in this world of mathematical fundamentals?
Well, we've still got some exciting territory to cover, like polynomials, equations that can be reduced to quadratic systems of equations, and then the fascinating world of inequalities.
Okay, let's start with polynomials. I remember them from algebra class.
Yeah.
But they always felt a bit abstract to me.
Right.
What exactly are they?
Yeah.
And why should we care about them?
So polynomials are expressions that involve variables raised to powers and multiplied by coefficients.
Okay.
They might seem abstract at first.
Yeah.
But trust me, they have a ton of real-world applications. In fact, they're used in fields like physics, engineering, computer science, even finance.
Wow. I had no idea they were so widely used. Can you give me some examples?
Absolutely. So, for example, in physics, polynomials are used to model the trajectory of a projectile.
Okay.
In engineering, they're used to design bridges and buildings.
Wow.
In computer science, they're used in algorithms for data compression and encryption.
Okay.
And in finance, they're used to model investment growth.
Okay, so they're definitely more than just abstract symbols.
Right.
They actually help us understand and solve real-world problems.
Yeah.
But how do we work with them? What are some of the key concepts?
One of the most important concepts is factoring. Factoring a polynomial means breaking it down into simpler polynomials that are multiplied together.
Okay.
And this can help us solve equations
Right.
and understand the behavior of the polynomial.
Right. I vaguely remember factoring from algebra class, but it always felt a bit like a guessing game.
Yeah,
Are there any strategies to make it easier?
definitely. One helpful technique is the factor theorem. It states that if a polynomial, let's call it px, equals 0 when we substitute a specific value for x, let's say x equals a, then xa is a factor of px.
So if we can find a value of x that makes the polynomial equal to 0, we know one of its factors.
Exactly.
That's pretty clever. But what if we can't easily find those special values?
That's where other techniques. Right.
It sounds like a lot to remember, but I guess the more you practice, the easier it becomes.
Absolutely. And it's worth the effort because factoring can really simplify things.
Right.
And help us solve more complex problems. But let's move on to another interesting topic.
Right.
Equations that can be reduced to quadratic equations.
Okay, that sounds a bit intimidating. What does it mean to reduce an equation to a quadratic?
Sometimes we encounter equations that look complicated at first glance.
Yeah.
But with a bit of algebraic manipulation,
Mhm.
we can transform them into quadratic equations,
Okay.
which are much easier to solve.
So it's like putting on a disguise.
Yeah,
And then revealing the true identity underneath.
exactly.
How do we know when an equation can be reduced to a quadratic? And what kind of tricks do we use?
Well, one common technique is substitution. For example, let's say we have an equation like x plus 1 plus 2x plus 1 equals 0.
Oh, yeah.
If we substitute y, x plus 1, the equation becomes y plus 2y8 equals 0, which is a simple quadratic equation.
I see. By making a clever substitution.
Right.
We can simplify the equation and solve it using familiar methods.
Exactly.
And then once we solve for y, we can substitute back to find the solution for x.
Exactly. It's a powerful technique for tackling equations that initially seem quite complex. Now let's shift gears and explore systems of equations.
Okay, I remember those from algebra class. They involve multiple equations with multiple variables, right?
That's right. And the goal is to find values for the variables that satisfy all of the equations simultaneously.
Okay.
It's like solving a multi-layered puzzle where all the pieces have to fit perfectly.
I remember struggling with those, especially when there were more than two variables.
Yeah.
What are some ways to approach these systems?
There are a few methods like substitution, elimination,
Okay.
and graphical methods. Each method has its own strengths and weaknesses.
Right.
And the best choice often depends on the specific system you're working with.
So it's like having different tools in your toolbox
Exactly.
for tackling these systems.
Right.
And I guess systems of equations have real-world applications too.
Definitely. They're used in fields like engineering, physics, economics,
Wow.
even in everyday life.
Real.
For instance, you might use a system of equations to figure out the optimal mix of ingredients for a recipe,
Oh, wow.
or to balance a budget.
Okay. Systems of equations are starting to seem a bit less scary now.
Yeah.
What about inequalities? Those always felt a bit tricky to me.
I understand. Inequalities can be a bit more challenging because their solutions often involve ranges of values rather than specific numbers.
Okay.
But they're incredibly important for understanding concepts like optimization,
Right.
constraints, and probability.
Right, because in the real world, we often deal with situations where there are limits or ranges,
Exactly.
not just exact values, like
Right.
I can only spend a certain amount of money,
Yeah,
or a recipe needs to bake within a certain temperature range.
exactly. And remember those intervals we talked about earlier? They play a crucial role in representing the solutions to inequalities.
Right.
When solving inequalities, we need to pay close attention to the direction of the inequality symbol
Okay.
and how it changes when you perform certain operations.
Like multiplying or dividing by a negative number, right?
Exactly. Those little details can make a big difference, but with practice
Yeah.
and a good understanding of the underlying principles, you can master inequalities
Right.
and use them to your advantage.
Well, I have to say, this deep dive has been quite a journey. We've explored the fundamental concepts of sets, delved into the fascinating world of numbers,
Yes.
mastered the art of manipulating expressions,
Right.
tackled those intricate polynomials,
Yeah.
unmasked equations, solved multivariable puzzles, and even navigated the intricacies of inequalities.
It's been an incredible journey, and I hope you've gained not only a deeper understanding of these essential concepts,
Yeah.
but also a newfound appreciation for the beauty and power of mathematics. Remember, math is not just about memorizing formulas.
Right. Or solving problems. It's about developing logical thinking,
Yeah.
problem-solving skills, and a sense of wonder for the patterns and structures that underlie our universe.
Beautifully said. And to our listeners, I encourage you to keep exploring the world of mathematics. Don't be afraid to ask questions. Seek out new challenges and embrace the joy of discovery. Who knows what amazing insights and connections you might uncover along the way.
Until next time, keep those mathematical minds sharp and never stop exploring the infinite wonders of this incredible subject.
Thanks for joining us on this deep dive. We'll see you on our next adventure into the world of knowledge.